and your member ID. And a reminder was sent, I believe, this weekend. They just, I don't know how many votes we have, but it would be nice to have a large number of members.
It'll be clear, sunny tomorrow.
Don't put it go.
That'll be nice.
So if you're a member, check your email and put in your votes for the board. We have a slate.
Big bottle of
Other
liquid soap up above the washing machine.
We need somebody to
Liquid
mute.
dish soap?
yeah.
Hey,
No,
Phil, you guys need to mute
hand
your
washing
audio.
Yes, we do.
Phil,
Would
you should.
mind?
Okay. So so I muted everybody. I'll unmute Linda, or rather ask her to unmute herself. I cannot. And speaker, where do you go? Kevin, okay. So then at the right time, I will make Kevin the host. So anyway, I just want to make sure that members are aware of the voting in case they missed the email. And I don't have any
I
other.
unmuted me.
Okay, good. I don't have any other major announcements other than we're still trying to look at what 2021 will be like in terms of activities. It's very likely we'll continue the Zoom series of lectures. We've been in communications with the park rangers on TAM, but they're non-committal on actual dates for member start parties. So that is basically where we're at. We'll have to update everyone when we know for sure about member start parties.
I notified the city of San Francisco about our third Wednesday lectures at the Randall. So that's been forwarded to the city, who's the one that is in charge of our being able to be there.
Yeah. And then we do have, we started in this year virtual start parties where astrophotographers and EVscope owners share their photos, but it's derailed into astrophotography meetup kind of. So I want to circle back and maybe split it into two meetings. One meeting for virtual astronomy and another one for astrophotographers. Because not everyone is interested in the technicalities of taking photos, they just want to see the photos. And there's another group that will eat up any detail on what equipment you own and how you did the whatever editing and tricks to get the photo looking like you did. So there's been a little bit of clash between those two interests. Just want to make sure we serve. Just want to make sure we serve the right people.
So Norman was the astrophotographer at our house, and since he's not with us anymore, I have a lot of equipment, and I can't. Some of it's just too heavy for me to pick up. But I've got cameras, and I had someone come and sort it out according to company and use. So I have a lot of astrophotography and telescope things to offer for sale at a very reasonable price when somebody's ready to think about that.
All right.
Yeah.
Keep that in mind for later. So later we have about 6-7 minutes. So I'll pass the baton to you unless there's any other news to share.
Are you speaking to me?
Yeah, I'll let you introduce the speakers unless there's
Hey, PJ,
Anybody else?
just for housekeeping, and Kevin, do you prefer everyone to, do you want to hold questions till the end? You may have already covered this. Do you want everyone to put their questions into chat so that you can handle them from that at the end? What's easiest for you?
From my perspective, it would be easier to hold them to the end. It's hard to keep the presentation logistics going and get chat questions and see hands being raised at the same time. I can make it work, but I would say if you have a question in the middle of the presentation, and just turn on your mic and feel free to interrupt. Otherwise, I'm happy to take questions at the end.
Sounds good. And if we ask people to put them in chat, then it's really easy for you to sort of take them in order and focus on the answer versus having to keep scrolling back and forth to see everybody's faces to see who's got their hand raised.
Sure. Yeah, that's fine. And I'll ask for help from Linda and others to make sure I get to all the questions in the chat.
Sounds
Yeah,
great.
I can help with that.
Yeah, they will.
So Linda, it's now your turn.
Okay. I want to talk about January 20th of 2021. The topic is mapping the missing matter in our universe, and the speaker is also from UC Santa Cruz, as is tonight's speaker, Sunil Simha. He's going to be talking about fast radio bursts, or FRBs. They were discovered only in the last decade. They last a few milliseconds and are an extremely bright source of radio waves. Fast radio bursts have been detected by the Australian Square Kilometre Array, Pathfinder, and the Sloan Digital Sky Survey. And you'll learn about the most recent research work that is being done by Sunil Simha and his group. Regarding tonight's speaker, Kevin Bundy, he's the assistant professor at UC Santa Cruz and the director of USC's Photon Horizon Initiative. It's a cross-disciplinary effort to advance the technologies of light. He's also the founder and principal investigator of the ongoing MaNGA Survey, which means mapping nearby galaxies at Apache Point Observatory, one of 3 core surveys in the Sloan Digital Sky Survey 4 project. Before moving to Santa Cruz, he was assistant professor at the University of Tokyo's Kavli Institute for Physics and Mathematics of the Universe. He obtained his PhD at Caltech, then moved to a Reinhardt Fellowship at the University of Toronto and a Hubble Fellowship at the UC Berkeley. He was a Tinsley Visiting Scholar at University of Texas, Austin, and for a recent PhD in North America considered unusually important to astronomy in 2009, and also the Dorothea Klumpke's Robert Prize in the Department of Astronomy at UC Berkeley in the year 2000. So tonight he'll talk to us about why do galaxies die, and about something you may not have heard of, Silicon Valley's Spectral Revolution, and how it's going to help solve a 100-year-old mystery. And I'm very, very happy to have our speaker tonight tell us about this mystery. Thank you, Kevin.
Thank you, Linda. What a tremendous introduction. I appreciate it.
I'll make you a host so you can share your screen.
Thank you.
Okay. Go ahead.
All right, let me see if I can get set up here. All right, I'm going to go ahead and get started. If there's any problem with the audio or the technical connection, please stop me and let me know. But it's a pleasure to be with you. I wish we could be in person, but I'm happy to be able to join you via Zoom and Zoom into your office or living room or wherever we are these days, and be able to share with you some of my excitement about the research that I'm carrying out. So thank you for inviting me to give this presentation. So what I want to do tonight is try to weave together 2 stories. And the first one is a story of science and a mystery about the death of galaxies. And I'll talk about what that means. And then the second story is really about how we go about addressing questions like this. And that's a story of technology. And I think we're at a really exciting time because, as I will argue at the end of the talk, I think we're on the verge of a kind of revolution in our ability to get spectroscopy from the sky and from everywhere else. And I think Silicon Valley and the Bay Area is going to play a role in that. And so I'm really excited about that technology development and how that plays into our ability to learn about the universe. So that's the theme and the overview for tonight. And I thought maybe I would start here. So this is an image that you're looking at. You want to talk about aperture fever. This is the Palomar 200-inch telescope, a 5-meter wide primary mirror. And this is, I think, a really good place to begin our story because this telescope represents the quest for knowledge, this deep desire to learn about the cosmos that we've had for so long, and how we've really built tremendous facilities to try to address that quest for knowledge and information. And for a long time, Palomar, which is down in between San Diego and Los Angeles, was the largest telescope in the world. But I put this photo up because it's also very personal for me. This is a telescope where I spent 75 nights observing as a graduate student, and I was very fortunate to be able to have that amount of time with this telescope. And I kind of feel like it was a teacher in a way. It was a mentor to me as I was going through graduate school, and taught me a lot about science and carrying out observations of the sky. But really the thing to capture with this image is the size. This is a very big telescope. And now I want to show you a picture of another telescope that's important to my life, to my career. And it's a smaller telescope. So this is an image of the Sloan 2.5 meter telescope, half the size in diameter of Palomar, but you can see quite a bit smaller structure all the way around thanks to other advances in technology. This is a 1990s telescope facility. And so much of the scientific story that I want to tell you tonight involves observations that were carried out or are still being carried out in some cases with this telescope. And so there's some irony here in the sense that the progress that has been made in addressing questions about the universe and about galaxy formation, which is my specialty, has benefited in a sense from going smaller, not always going bigger. So through miniaturization, as I hope to convince you, we've actually been able to learn more about the cosmos and about galaxies. And I see this playing out in the future, and that's, I think, very exciting because I believe that the future is smaller still. And so in the last part of the talk, I want to describe some of my excitement about photonics and what I call the spectral revolution. This is actually an astronomical device that you're looking at on the screen. And you can see we've gotten interested in scales that are even smaller still. Very small scales, nanoscales, and our ability to control light on the surface of a chip, much like we control electrons and electronics, is really developing rapidly. And I think that this technology is going to have huge implications for astronomy. So this device that you're looking at is actually an astronomical device. Those little etchings that you see in the chip are actually light waveguides. So photons travel through those etched channels and interact in desirable ways for the purpose of this instrument. So to me, this is really the future, and I think it's kind of interesting that the future is actually smaller still. So we love those big apertures. We certainly have aperture fever, but the story in this talk is about going small. So why are we doing all this? It does come back to this quest to understand it all. Here's a cartoon that I love to show. Cosmology, our understanding of the universe marches on. A long time ago, we looked out from our caves and our villages and we asked, where the hell did it all come from? And the modern astronomer looks at their data, probably on a computer these days, and says, where the hell did it all come from? And so, you know, that's still, of course, what we're doing. We're still trying to build better and better tools to figure out what the universe is all about. And specifically, this talk is going to be about galaxies and how galaxies evolve inside that universe that we're still struggling to fully understand. So the question that I really want to focus on tonight, the scientific question that's going to try to weave in with our development of technology and motivate future technology. The scientific question is why we have these two types of galaxies, why we have ellipticals, you're seeing one example on the left, and spiral star-forming galaxies, and you're seeing one example on the right. And I know that all of you as amateur astronomers look through telescopes all the time, or maybe not as often as you might like these days, but as much as you can. And you've probably noticed that there are fuzzballs and then there are spirals. And you may be wondering what makes these two different types of galaxies? Why do we have this dichotomy in the galaxy population? And that is a very old mystery. And the story really begins before Palomar. It begins, in a sense, with the Mount Wilson Observatory and the 100-inch telescope, which was the motivation for Hale's 200-inch telescope, because 200 is twice as big as 100. And I think literally that was the reason to build the 200-inch telescope, was to show it was bigger than Carnegie's 100-inch at Mount Wilson. But Edwin Hubble, the famous Edwin Hubble, used the Mount Wilson 100-inch to do amazing things. And one of the things that he did was just take images of galaxies, photographic plates. And he, of course, noticed that there were these two basic types, ellipticals and spirals. And he organized them into this famous tuning fork diagram that I imagine many of you are familiar with. It's a classification system that Hubble invented. There were others at the time, but Hubble's diagram survived to the present day and is still a way we think of organizing the shapes or the morphologies of galaxies as they appear in the sky. And in Hubble's way of thinking, there was a sequence where you had ellipticals of different ellipticity, and then two tines of his fork for the spiral galaxies. The upper tine being more dominated by a central bulge, and the lower tine by a bar. And essentially, this is the question: where does this diagram come from? Why do galaxies populate this diagram in this way? And are they evolving from one side to the other? Where does it come from? How did they get started? These are essentially the questions that astronomers studying galaxy formation have been wrestling with for 100 years. And we still don't know all of the answers. We've learned a lot. But the modern picture, I would say, of this tuning fork diagram and this classification system really comes down to focusing on this kind of general difference between ellipticals and spirals. And so this is the challenge. This is the question that I want to focus on today. And I want to talk a little bit about the progress that we've been able to make and show you some of the work that I've been involved in that's allowed us to understand where these two different types of galaxies come from, and specifically how they're evolving and what that means. So to understand why we've been able to make recent progress, I want to go back to Palomar, and I want to start weaving in this story of technology as well, because the development of our understanding of galaxies is tightly connected to the technological tools that we have at our disposal, as are most things in astronomy, maybe science generally. So I want you to understand the power of going smaller. And to do that, I want to show you this image that indicates how big things are. So what you're looking at here is the Palomar 200-inch telescope, and it's tilted way over to the side. So this image is actually looking down the barrel, so to speak, and you're seeing the primary mirror here and the reflection at the bottom. And then this is the prime focus cage. So in these kinds of telescopes, the first focus is the prime focus where the light is bouncing off. And before it gets sent to the side, as you might be more familiar with in a Dobsonian telescope, say, you have a prime focus position. And the observer would often sit in this prime focus cage as the telescope tracked across the sky in freezing temperatures and carry out their observations. And what I want to indicate with this photograph is really the size of the focal plane, which is sort of indicated by the yellow scale bar there. That's roughly the size of the focal plane. So we're used to, with amateur telescopes, we're used to having an eyepiece, and we put our eye up to the eyepiece and we see what's in the telescope. If you wanted to look at, if you wanted to use an eyepiece on Palomar or a similar large telescope, the focal plane is so big that you could put your eyepiece and then move your head around, and everywhere within that ½ meter or so, maybe 2 feet diameter focal plane area, you would be collecting light, you would be seeing an image that the telescope is making. So the focal plane is really enormous. And this has big implications, because what it means is that if you want to build instruments that process the light being focused by large telescopes, you've got to build big instruments. And so much of the progress that we've had in recent decades and even into the future comes from being able to make big instruments. This is a overlay of a diagram of a new camera that's going on a new telescope, the Rubin Observatory. And here is a person to scale. So you can see that we require instruments that are person-sized or bigger in order to capture all of the light that's coming from a telescope like this. And so you can see that this is a challenge for astronomy, because it's hard to make something that's this big. Imagine the pieces of glass, the weight, and the expense that's involved in making something so massive to be able to process all that light. And so this represents a challenge. And in recent years, again, by thinking about going smaller, we've been able to address this challenge in some really interesting ways. And so going from Palomar, I want to talk next about SDSS, the Sloan Digital Sky Survey, and this smaller, but in some ways more powerful 2.5 meter telescope. And so what SDSS did, again, probably a name that you're familiar with, one of the things it did was conduct the largest ever survey of nearby galaxies. And it first utilized CCD technology to do an all digital image of the sky. That's the D in SDSS. And then it followed up that digital image with a spectroscopic survey. And that combination has been extremely powerful. First, you get the deep images that tell you where your interesting objects are. And then if you know where they are, you can follow them up with spectroscopy to really learn about the details inside the sources you care about, in this case, inside galaxies. So in order to make this work, imagine that big focal plane. For the Sloan telescope, it's bigger still. It's about 1 meter across, about 1 yard across. And the innovation in the 1990s was to use optical fibers. So forget about trying to process all the light from such a large focal plane. Instead, let's use optical fibers, and we will put those fibers on the objects that we care about. And we'll only process the light that's guided through those fibers. And this was a major innovation, because it allowed us to study 600 objects at a time, 1,000 objects at a time, eventually 1,400 objects at a time. But we could do that with a smaller instrument. We could do that with a spectrograph that didn't have to be so enormous in order to be able to process all the light from the focal plane. So that has enabled very large surveys of galaxies. And SDSS carried out a survey of 1 million galaxies in the nearby universe. The fruits of that effort are shown on this screen. And so you're looking at a map of galaxies nearby. And what do I mean by nearby? If you're familiar with redshift, this is out to a redshift of about 0.1, 0.15. That is the distance that light would travel in about 1 billion years. So for astronomers these days, that's considered the nearby universe. For our everyday lives, that's a very long ways away. But even still, galaxies at the most distant edges of the Sloan survey, the light from those galaxies left about 1 billion years ago, okay? Now, when I look at this image, what I see reminds me of like neurons or, the structure of the brain or something like that. And indeed, that's a pretty interesting observation. But what you're seeing is lots of little dots, and each dot is one of those 1 million galaxies. And then this is in 3D and it's been projected in 1 dimension so that we can see the structure. So this structure is all real. This is how galaxies are arranged in the universe. And every single dot here is an actual galaxy that was recorded by SDSS. The nature of this structure is extremely interesting. It tells us about gravity. It tells us about how matter forms in the universe. It tells us about the universe itself. And there have been many exciting discoveries from investigations of that structure in SDSS. That's not what I'm here to talk about, however. What I want to talk about is the individual galaxies inside that structure. And again, the brilliant thing that Sloan was able to do was to get a spectrum for each of those 1 million galaxies. Very good spectra, very high quality spectra. You're looking at an example here on the screen. And a spectrum, just to remind you, is kind of like the prism that you would get if you were to, or the output of light from a prism. It's the light broken down into its constituent parts as a function of wavelengths. So on the screen, this is flux on the y-axis, light intensity, you might think of it as a function of the wavelength of the photons that you're studying. And the key thing is that all of that structure there in the spectrum is giving you important information about each of those 1 million galaxies. So by studying the spectrum, we can learn about star formation, black holes, supermassive black hole accretion, the chemistry of the galaxy, the mass of the galaxy, the velocity information in the galaxy, what it may have looked like in the past. All of this comes to us from this incredibly rich spectral information. And you can imagine that being able to have that kind of information for 1 million galaxies was transformational. And coming back to our question at the top, why are there these 2 different types of galaxies? SDSS made a major advance. It taught us through this diagram that I'm showing here on the slide that dichotomy in galaxies that Hubble noticed, ellipticals and spirals, in large part has to do with whether the galaxies are alive or dead. And coming back to my definition of a dead galaxy, what I mean by that is it forming stars? And so astronomers often refer to red and dead elliptical galaxies. What Sloan taught us is that the ellipticals don't have ongoing star formation for the most part. They populate this part of a color magnitude or color mass diagram of galaxies where they live on what's called the red sequence. That means that their average stellar colors are consistent with no hot, young, bright blue stars. And that's what you would expect if a little time has passed and no new stars have been formed, because those hot blue stars don't last very long. They burn out of fuel very quickly. And so if there aren't new ones to take their place, you're blue, lively, youthful star-forming galaxy suddenly turns red and dead. So those youthful ones are down here in what we call the blue sequence, and they look like the images shown on the right. They have more disk-like components. They've got the spiral structure. They've got knots of star formation. They are alive. So really, Sloan helped us understand this dichotomy between the two galaxy populations, and that helped us sort of map out the demographics of nearby galaxies to understand this. But we're left with questions. So we can understand something about the dichotomy between the two populations, and we can learn more information about the nature of the way that stars and the different types of galaxies form, the gas properties, etc., using all of that information in the spectrum. But there's something that is missing with the SDSS. And what's missing is the internal physics, the internal properties of what's going on. So remember, we've got this spectrum, we've got 1 million of them. That gives us amazing global statistics for the population. We have all that information, but we're treating the galaxy like it's a single point. So each of those fibers that we've put down is just sampling one galaxy. And the information that we get, we assume corresponds to that one galaxy, but we've missed what's going on inside. Galaxies are not point sources. We know that they are complicated, beautiful, rich structures, very complex systems that have a lot going on inside. And so when surveys like SDSS and others put a fiber down on a galaxy or a slit to get a spectrum, they may only be seeing the center of the galaxy. Or if they're able to collect light from the entire galaxy, it's all the light added together. And so that one spectrum has been very powerful. It's taught us a lot. But what we really want is to have a spectrum at every location across the galaxy. We want to be able to peer inside galaxies if we're going to understand how they work. So this type of observation, this spectroscopy with an integral field unit, that's sort of the jargon that we use in astronomy and IFU, or resolved spectroscopy, meaning that I've spatially resolved the different parts of the galaxies and gotten the spectrum at every location. This is really the most powerful way that we can look inside the galaxies and figure out what are the processes that are actually causing these differences in the population. We know what the differences are. What's the physical mechanism that makes them? What kills galaxies? This is the kind of observation that we need. Now, the problem when I came around was that we had instruments that could carry out this kind of resolved spectroscopy, but there was no way to do it at scale. You could do this sort of one at a time. So there were samples of maybe 100 galaxies measured this way, maybe 200, but we couldn't combine both the wealth of information that would be possible if we could get spectra like this, resolved spectroscopy, with a large sample. And so that motivated the MaNGA survey. And this was something that I developed as a late postdoc, so just before I moved to Japan as a faculty member. And it has been an exhilarating experience to be the leader of this MaNGA project. So MaNGA, as Linda mentioned, stands for Mapping Nearby Galaxies at Apache Point Observatory. And it was actually a follow-up way of using the fibers from the Sloan Digital Sky Survey. MaNGA was an instrument that was deployed on the Sloan telescope. And so that's why that little 2.5 meter also holds quite a special place in my heart. Another one of my telescope teachers. So I want to tell you about MaNGA. I want to tell you about the technology that enabled MaNGA, because it sets the future for what we're excited about to come. And I want to focus on one of the discoveries that MaNGA has made on this question of what kills off galaxies, what makes red and dead galaxies red and dead, and what is the physical process responsible for the dichotomy in the galaxy population. So MaNGA is really about using fibers in a different way. And so coming back to the technology, I just want to point out that optical fibers are thin, brittle little guys. And here's an example of a photograph of an optical fiber at the bottom and a human hair at the top. So this is kind of like working with human hair. And so the challenge with optical fibers is that they're small. You can still use your fingers to manipulate them, but imagine that you have hair, only it's a little more brittle and can break. And you've got to figure out how to arrange the fibers together to get the kinds of observations that you want. And so for MaNGA, what we attempted to do, what we did, is we took the fibers that were available from the Sloan telescope and the Sloan instrument, and we bundled them together. Instead of having individual fibers, one fiber per galaxy, we made bundle arrays, and we created little integral field units, little IFUs. So we needed to make them very tight packed and very regular. And we created this complement, this suite of what we call fiber bundles that you're seeing here on the screen. The different colors are just to kind of guide the eye. They don't mean anything in particular, just to show you that we had a range of different bundle sizes. The largest one had 127 fibers put together, and we had 17 simultaneous bundles that we could deploy on the sky. So that was a big breakthrough, because what it meant is, for the first time, we were able to obtain multiple resolved spectroscopic observations of galaxies at once. We could do 17, and that allows you to start really building a large sample. So we could get the sample size that SDSS taught us was so important, and the additional information about what was happening inside galaxies. And it was all about making these bundles. So here again, the technology was about going small, and we were really working at the micron level. And the essence of making MaNGA work was about very careful, advanced machining technologies. And I just thought I would show a slide showing you the ferrules. So these are the metal tubes, if you like, that hold the fiber bundles together. And we designed these and machined them so that the inside starts off like a cylinder, like a hollow cylinder, and then it tapers down to a smaller and smaller size. So you're inserting this bundle of, say, 127 fibers, and they start to get squeezed together. And then we slowly machine the circle, and it transitions into a hexagon. And what we discovered is, if we could make this very smooth and very precisely machined, then we could quite straightforwardly make lots of these fiber bundle arrays. And so what we ended up with is a series of instrumentation, a series of these IFUs with excellent regularity, closely packed together, about almost perfect for packing circles inside a hexagon. And that's really important, because it means that we have high quality data. It means that we sample the galaxy that's going to be placed inside one of these fiber bundles on the sky in a very regular way. We can move the telescope slightly and kind of map out the internal structure using this kind of device. But again, it was about being small and being precise. So just a couple of pictures to show you how this works. Here's some dental tools being used to line up fibers. This is the output part, actually. This is the part that goes into the spectrograph to be dispersed and processed. But you can get a sense of how small and challenging it is to work with these optical fibers. But then once you have the bundles built, you essentially plug them into plates that sit in these cartridges. And there are 10 or 12 cartridges available for a given night. So the cartridges get plugged with the plates that you want to observe that night, and they get plugged during the day. And literally, this is about using your fingers. There are technicians that take the ferrules and the fiber bundles and put them in the holes in this aluminum plate that's been drilled for a particular location on the sky. And then throughout the course of the night, those cartridges get mounted to the telescope, and the telescope points at the right location. The light comes down and hits those fiber bundles, gets guided to your instrument, and away you go. So for MaNGA, each plate is 3 degrees in diameter on the sky. That's 6 full moons across, and we get 17 galaxies per plate. We have a number of other calibration bundles and so on that we have on there as well. And this worked amazingly well. So here's some shots of the facility. You're seeing again the famous SDSS telescope. Here are plates that have already been observed, some cartridges that will be plugged and available later that night. And one of the plates up close where you can see the holes drilled into the aluminum for future plugging. Now, this is a video that may or may not come through for some of you. I hope it does. You can see one of the technicians, one of the plate pluggers, working on plugging a plate. This is not a MaNGA plate, actually. This is another SDSS survey called BOSS that had 1,000 individual fibers, each one plugged by hand. So she and her team would work several hours a day, 6 hours a day, plugging plates, getting them ready for the night. And she was very fast. Here's a cartridge which has been plugged. It's ready to go. The cartridges are stored in this room that has a door on the outside. So at night, the observer can pull out one of the cartridges, put it on this cart, roll the cart down to the telescope, and mount the new cart. Take the old cartridge off that's just been observed, mount the new cartridge on. The telescope gets pointed in the right direction, and you're off to the races. So this is how SDSS works. It's how MaNGA works. It's how you build a very efficient sample and do it at a reasonable cost, because you notice we don't have robotics. We don't have, we're using people power here, and that is part of SDSS's success. So I want to just give you a flavor of what the MaNGA data look like. So here is our first commissioning plate from back in 2014. And you're seeing the footprint of those fiber bundles outlined with the white hexagons and a motley crew of galaxies that we observed on that first plate. And you can see some of them are what I call red and dead. That they're in images, they actually look more yellow, but galaxy formation people call them red and dead. And you can see blue star-forming galaxies, ones that have very clear spiral structure. So even in this one sort of random selection of MaNGA targets, you can see the very question that has been guiding me, and that we've started with in this talk. So the good news is that MaNGA is complete and has been a great success. I'm happy to report that in August of this year, we finished the survey. 10,000 galaxies observed in 3 dimensions, if you like. And we have made an array of really exciting discoveries, all kinds of topics in galaxy formation. And it's just been such a pleasure to be part of the team and to be able to lead this really exciting project. In a way, we're kind of not even halfway through the data. We've collected all the data, but now the fun of analyzing it and learning about it, doing science with it, is really underway. Most of this data is public, and all of it will be public in about a year or two. So you're welcome to go online and look for it. In fact, we have a wonderful interface that allows you to point and click on any interior region of one of our target galaxies and see the corresponding spectrum. And so I invite you to play with that and peer inside galaxies yourself. So let's come back to this question. Why do galaxies die? And let me tell you how MaNGA has, one of the ways that MaNGA has added to the story. So remember, we have these two types of galaxies, and SDSS1 taught us by having 1 million sampled that this dichotomy is really about whether there's star formation occurring. And the elliptical galaxies do not have ongoing star formation for reasons that we don't understand. The spiral galaxies still do. So why do the spiral galaxies die out? And we know that they do because we can look at the galaxy population at earlier times, and we can see this demographic pattern that was clearly mapped out with SDSS. We can see a change. And we can see that as we look back in time, there are fewer and fewer of those red and dead elliptical galaxies and more disk galaxies. So it seems like over cosmic time, a set of processes perhaps is killing off the star-forming galaxies and creating these red and dead ellipticals. One of the first things we did then in MaNGA was to take some of that early data and look at these red and dead galaxies. And I'm showing examples here on the screen of what we saw in the images that we used to target the survey. And you can see there's not much apparent that's going on in these images. These galaxies are very smooth in appearance. You don't see much structure. You don't think that there's a whole lot apparent that's happening. They look dead. But we noticed a population that when you looked at these galaxies with MaNGA, and you looked at certain key spectral features, you saw these very interesting patterns that emerged. So what you're seeing here on the right-hand side for each of those images on the left is a mapping of ionized gas, specifically the H-alpha ionized emission line. And you can see that these galaxies are not dead at all. They've got something inside that is interesting and maybe a clue as to what's going on. And we noticed that these patterns often connect in the center, and they are typically bisymmetric in appearance, very faint, barely detected in some cases, but surprisingly common. We find this in about 5 to 10% of the red and dead galaxies that we look at in the MaNGA data. So what are these things? And could this be a clue as to what makes this kind of red and dead galaxy? So we really dug into this particular prototypical system to be able to ask some of these questions. And this is a galaxy that we studied in gory detail. And I just want to give you some of the highlights that we learned thanks to the MaNGA data on this galaxy. It happens to have a companion that seems to be donating material to it. You can see that in the background image. You can see the tidal arms that are connecting probably stars and gas between these two interacting galaxies. So the lower mass system is likely being torn apart and having some of its material sucked into the larger galaxy. But coming back to these patterns, we noticed that they were in red galaxies, and we noticed that they seem to look like flows of material coming from the centers. And so in studying that galaxy and the population that we discovered, we decided to call these red geysers. And really the question of red geysers is, are they indeed examples of outflowing material in otherwise dead and inactive galaxies? And if so, we believe that they may be particularly interesting because these kinds of outflows could be what is keeping gas in these red and dead galaxies from cooling and from eventually forming stars. So this mechanism may be important for keeping red and dead galaxies red and dead long into their futures. So by studying our prototypical object we really tried to understand, are these outflows? And if so, how much energy is contained? Is there enough energy to have an impact on the rest of the galaxy and to keep gas that would otherwise cool and form stars from doing so? And we found that these are very high gas velocities. It appears that the material inside these outflows, a portion of it, is moving at velocities faster than the escape velocity of the host galaxy. So what that means is that some of this material is actually blowing out of the galaxy altogether. And that sounds dramatic, but these are really the key thing about this phenomenon is that it's kind of a weak one. It's a faint low luminosity effect, but it's common. And so it may be a really important clue for understanding the late time evolution of such red and dead ellipticals. So what we think we're seeing again is related to accretion onto the central supermassive black hole of these host galaxies. And all galaxies really above a certain mass are expected to host supermassive black holes 1 million times the mass of the sun, 1 billion times the mass of the sun. And that black hole sits there at the centers of galaxies. For many of them, it's hardly noticeable. But when a bit of material falls in and starts orbiting and eventually decaying and falling into the black hole, there's a tremendous amount of energy that can be released. That's how you get a quasar. That's how you get active galactic nuclei. But there are other phases of black hole accretion that can be quite weak. And so we think that that may be what we're seeing here with the red geysers, a little transient phase of accretion onto the central supermassive black hole, which is driving just enough hot ionized gas flows into the rest of the galaxy to keep it hot, to keep that whatever gas is left over from being able to cool and form new stars. And so in this way, these red geysers could play a role in keeping red and dead galaxies red and dead. So here's our famous pair system. And we've got a little sort of artist's rendition of what we think these galaxies should look like. And this is an active topic of research, both in my group and in others now, really following up on this discovery. You know, we want to know more about this red geyser phenomenon. If it's 5 or 10% of the galaxies that we happen to see in our particular survey, then what does that mean for the rate at which this phenomenon might be turning on and off among all red and dead galaxies? What is the nature of the interaction between the different phases of gas, the outflows of material versus gas that might otherwise be cooling? So this is quite an active topic, and we still have more to do. But you know, this could be very exciting, and it again comes back to our ability to peer inside large numbers of galaxies and be able to see otherwise hidden phenomena. So red geysers may be an important part of this story about why there are two types of galaxies, and specifically what kills galaxies, what turns off their star formation, and what keeps it off at late times. But we're left with questions. And one set of very interesting questions is, does such a phenomenon happen early on? Remember, the galaxies that we're looking at in MaNGA are those nearby galaxies. They're within, 1 billion years of the present day universe. So that's not a whole lot of time compared to a 14 billion year old universe. What happened in the past? What about the earliest galaxies that shut off star formation and became ellipticals? Did they have red geysers as well? And just more generally, what else is determining how galaxies form and regulate themselves as they emerge from the cosmic matter field, if you like? How do galaxies form in that cosmic web? How do they do that at early times when the universe was mostly gas? And how does that help us understand the universe and the distribution of matter within inside. So these are some big questions, and they really push us to thinking about the universe at greater distances, at earlier times. And so let me now transition into thinking more about the future. And I want to come back and try to weave in the technology angle, because I think that you'll see that one of the ways we're going to meet this exciting opportunity with the future of astronomical data is through some of the new technologies that are being developed. So in the next few years, questions like this are going to be very exciting, because we're going to have this incredible enhancement of imaging data, photographs of the sky that are really going to be a deluge of big data. And I'm thinking here primarily of what you may have heard of, known as LSST, and recently renamed the Vera C. Rubin Observatory. And this observatory is a dedicated facility with that enormous camera that I showed in comparison to Palomar early on in the talk. That camera and this observatory is going to take incredible amounts of images of the sky. 3 terabytes per night are going to be obtained by LSST, the survey that this observatory will carry out. And all of that data is going to mean we're going to get something like 1 billion galaxies surveyed out to very large distances. It's right at the era of peak galaxy formation, where we can address these really interesting questions. But we have a problem. And the problem is that we have so many images, but we need that spectroscopy in order to get the rich information about what's going on inside the galaxies, and also just locating them in distance. And obtaining 1 billion spectra is beyond our technical capabilities at the moment, and certainly beyond our budgets. So remember, SDSS was 1 million spectra. We're not talking about a need for 1 billion objects with spectroscopy. And there is no foreseeable easy path to get there. We need a technological breakthrough. At the same time, imagine doing resolved spectroscopy. Imagine putting bundles on some of these objects. We think that we're going to have adaptive optics technologies improve, if you're familiar with that, which will allow us to get even better resolution for some of these distant galaxies. Even a small fraction with MaNGA-like resolved spectroscopy is currently beyond our capabilities. So what we need is an order of magnitude increase in our ability to collect spectra, to collect astronomical spectra. We need to be able to measure not 1,000, not 5,000, but 50,000 or 100,000 simultaneous spectra. So how are we going to do that? We have too much imaging coming. We have not enough spectroscopy. We don't have the instruments capable of keeping up. And we don't know exactly how we're going to get to 50,000 or 100,000 simultaneous spectra. Well, I'm an optimist, and I think that the answer is going to come from the Spectral Revolution and from Silicon Valley, probably among some other places and institutions. But Silicon Valley and the Bay Area to the rescue. I do believe that there is going to be a revolution in the technology that deals with spectra, and that is going to provide a tremendous opportunity and address this challenge. And I think history shows that this can happen. So the era that we're entering with large data, big data in astronomy dates back to another connection between Silicon Valley, the Bay Area, and astronomy. And this is what you might call the first light revolution, when digital cameras began to change the world. So I'm really thinking of Silicon Valley in the 70s, the development of microchips and microprocessors, and the simultaneous and related technology development of CCDs. This is really about being able to capture photons and convert them into electrons that we can then study digitally. And the technology here involves the ability to engineer at the micron scale. So as Silicon Valley is developing this technology for computing, it leads to CCDs, and astronomy comes in and takes enormous advantage of CCDs to carry out surveys of the sky. So you're looking at a picture of the camera for the original Sloan Digital Sky Survey, which was one of the first mosaics of early CCDs. And that's what put the digital in the Sloan Digital Sky Survey. The next generation involved the optical fibers and spectroscopy. But this was the first connection. And the story, it gets more interesting in a way, because on the Silicon Valley side, we have this connection between the ability to use CCDs to get cameras in your cell phone, and also to generate video that entertains us, that allows us to communicate, that allows me to give a Zoom recording and a Zoom presentation to you tonight. So that technology, of course, has really driven video. It's driven the need for a very powerful internet. And that has also been enabled by the availability of fast imaging data sets and machine learning, which again is something that astronomy has always been a part of and has helped to develop. So we have these two connections between small technology that allows for bigger data, and then connections between the way that those data are shared, astronomy and Silicon Valley. In the second light revolution, I think that it's going to be nanospectroscopy that will change the world yet again. And here what I'm really thinking about is nanotechnology and optical computing. And so if the first revolution was about micron engineering, we're now at nanometer scale engineering. And this is really exciting from a computing point of view, because it means that we can shrink beyond some of the limits of dealing with electrons and use light to carry and process information. And there's perhaps a connection here with quantum computing as well. So the ability to control light and to engineer structures at nanoscales lets us miniaturize astronomical instrumentation even further. And so even though we're still interested in those large telescopes, the instruments are getting smaller and smaller. So just with a few slides to go, I want to introduce you to photonic nanospectrometers. And here is the problem with spectroscopy in the big data era, why we can't get enough spectroscopy. It's because conventional imaging spectrometers are big. Same problem that we saw back with the Palomar telescope and trying to process all that light from the focal plane. If you want to do that, you need to build a very large instrument. And so here is an actual instrument design being displayed on the screen with humans to scale. And something like this would cost 60, 80, $100 million. It will give you approximately 100 galaxies at a time. So if you want to do 100,000 simultaneous spectra, even if you use optical fibers and the conventional technology that we have, you're looking at a cost of $1 billion, which is far more than your whole telescope and observatory. So it's just out of touch. The hope is that photonic spectrometers allow us to shrink all of this down and to use the same sort of microprocessing etching techniques that Silicon Valley has developed to print spectrometers on a chip, if you like, and be able to dramatically reduce their size and cost. So this is exciting for astronomy. It's exciting for many other applications that could benefit by having ubiquitous, cheap, powerful spectrometers. And you're looking at one example of a variety of research groups that are pursuing nanospectrometer designs. And so this one has these really interesting nano patterns that they're non-intuitive, right? They don't even really mean anything. But as light passes through such a structure, it interacts with those structures. And by carefully designing them with a computer, of course, and being able to control nanometer scales, you can make the light disperse, focus, and have other properties that are of benefit, including spectroscopy. So this is an example of a nanoscale photonic spectrometer from a few years ago. Here at UC Santa Cruz, we've begun a collaboration with Holger Schmidt in engineering to use one of the devices that he's developed. And this is a picture of him holding it. This is an on-chip lab, if you like, that processes light and tiny fluid samples at the same time. And so by using this kind of technology in a different way, we've just begun working on an idea to turn this into a spectrometer. And you can see that this comes about by looking at patterns, interference patterns that are created within these etched channels on such a chip. And by studying how the spatial profile of the pattern changes with wavelength, you can then try to back out the spectral information. So this is yet another approach, another option for developing these photonic nanospectrometers. And in general, this has motivated a concept to try to bridge together different groups that are working on technologies of light. And so at UCSC, we call this the Photon Horizon Institute. Our initial focus is on astrophotonics, the use of photonics technology in astronomical instrumentation. But we think that this has really broad applications. We really do believe that a spectral revolution is coming. And so our initial collaboration is astronomy, UC Observatories, which is headquartered here in the School of Engineering, but we've got people from physics, from biomolecular engineering, from chemistry, that are all interested in this technology and the overlap. And the idea is to develop photonic technologies that can benefit scientific instrumentation, that can change the way we diagnose and monitor health, and may have other applications. So, my vision, my dream would be to have a spectrometer in every cell phone. Think about the information that you could learn about the world and how that would change the way we interact with it, just as having a camera in every cell phone has changed the world. So we're excited about this. We're excited about opportunities. We're looking for partners, both in industry and commercial enterprises. So if you have excitement about this and this overlap between technology, science, health, computing, please let me know, get in touch. We'd love to talk more. Last thing I want to mention before I wrap up is that many of us are also thinking about how we can use this technology for COVID-19. And so even though we are astronomers and we don't know anything about epidemiology, we are actually pursuing the application of some of this technology to a rapid COVID-19 test. So that just gives you a sense from the scientific community of the urgency that we all feel in trying to deal with this problem. Even though the vaccine is coming, it's great. This kind of testing is probably going to be useful for a while, and so we're pursuing that as part of this photonic initiative. So let me conclude there. What I tried to do tonight is to weave together two stories. And both of the stories are really motivated by trying to understand the mysteries of the universe. And the one that I talked about that has got me motivated for a long time was the death of galaxies, why we have these two types of galaxies, why star-forming spirals seem to transform into red and dead ellipticals and never return. And so I talked about how the technology of optical fibers, of bundling those fibers to make IFUs, which give us resolved spectroscopy, has allowed us to peer inside galaxies and discover a clue that may be important for why it is they die and stay dead. And we call those red geysers. Those are outflows of material that we've been able to detect in the MaNGA Survey that we believe may be part of the story for why these galaxies die and stay dead. And then at the same time, I've also talked about technology, and I really believe that our future depends in a sense on this evolution from very large facilities, very large instruments, to smaller, more precisely measured, more precisely defined instrumentation on the micron scale, and finally at the nanometer scale. And that by taking advantage of those technological strengths and developments, we'll be able to build more powerful instrumentation that will help us address this question about the nature of galaxies, be able to collect more spectroscopy from the universe, and perhaps have applications in the everyday world as well. So I will stop there and take questions. Thank you so much.
Hello.
Thank you. I heard a voice.
Hello. Hi.
Hi there.
I was kind of wondering, I sort of got the impression that you haven't come to any conclusion yet regarding what causes the difference, even though you've studied so many galaxies in the older method.
I think
You don't seem to have come to any conclusion as to why there are these two. At least I didn't hear you say anything like that.
Yeah, I think we still don't know the full answer. So what we've discovered in MaNGA is part of the story, but we need to now go and look at more distant galaxies and collect more information if we're going to figure out the whole picture. And so this is still a very hot, raging topic in astronomy and galaxy formation circles. What causes this transformation in galaxies?
Yeah, but you don't seem to even have any tentative conclusion.
Well, I'm not sure that would be a fair statement. I focus primarily on this red geyser phenomenon because
what does that tell you?
So the truth is that there are probably multiple mechanisms that are at play here, and in this field, what we typically do is divide the triggering of the transformation from a maintenance process. So there's essentially two problems. One is how you initially shut off star formation. And then once you have it shut off, how do you keep it from coming back? And so the second problem is more the one that the red geysers address. It's more about the late time evolution of these elliptical galaxies and why they never go back to becoming star forming. Red geysers could be really important there, but they may not be so important in the initial event, which shuts off the star formation. And so that may have something to do with quasars. It may have something to do with mergers of galaxies. It may simply be that galaxies change their morphologies in a way that prevents as much star formation as might happen. But we don't know. And so there's a lot of theories, and it's still a very active topic. So I can't conclude because we don't know.
So have you published any papers regarding your study that we could perhaps read?
Of course. Yes. Most of my papers are on this topic.
Okay. And then regarding the new photonics, that I must admit I didn't understand how you could extract information from these waveguides. I didn't hear you say anything that helped me to understand how you could extract information.
The idea that we're working on here at Santa Cruz would convert spatial interference patterns into spectral information.
Is that possible? That you mean that's possible somehow?
Yes. So the way that these devices work is they take light from a fiber and they send that light through this channels on a chip into a little cavity. And when the light enters that cavity, it begins reflecting off the boundaries and interfering with itself. And those that interference leads to spatial patterns. And the shape of those spatial patterns, the nature of the patterns depends on the wavelength. So if you can study how those patterns behave and you can observe them, then you can infer how much light as a function of wavelength you had coming in. And that is what a spectrum is. So it's a way of translating spatial information back into spectral information.
Okay, I must admit I don't fully understand that, but maybe I will later if I read some of your papers.
Well, this is very new, so we don't have any papers on this yet.
Oh.
But if you want to follow up with me, I can point you to some examples of actual devices that have been built on similar ideas.
Okay. So I'm going to stop talking so somebody else can ask a question.
Thank you for your questions.
Hi, I have a question. I was under the impression, I don't know why I have this impression, it could be something I read long ago, that the reason spiral galaxies stop their star forming had to do with them running out of fuel. Is that a possibility? I didn't hear you say anything about that, so I don't know if that's just something I falsely remember, or and also the rotation, not rotation, but my understanding was that the spiral arms are due to and then the way the gravitational, it had to do with gravitational waves in spiral galaxies. And do they just disappear for elliptical? What happens to these mechanisms?
Yeah, those are both excellent questions. So let's take the first one first. This was the hope when people began to really try to investigate how you got the SDSS population. Let's build models and let's run a simulation. Let's see if we can reproduce what we see in that 1 million sample. And the hope was, if you just let the galaxy continue to form stars, eventually it'll run out of fuel. And then there you go, you'll have your red and dead elliptical. So that was the hope, but it didn't work. And the problem is that it doesn't take much star formation to make a galaxy look like a blue star-forming spiral galaxy. Most of the stars in even most spirals are old, but it just takes a little frosting of new material, and you really notice it because those young, recently formed stars are very bright, and they dominate the light that you see. So the problem was there was no way to keep just that little bit of gas from cooling and forming stars and completely shutting off the star formation. So you needed additional processes, and that's where the red geysers might come in. You need some kind of feedback mechanism that injects energy into the ambient galaxy and the ambient gas and keeps that from cooling and forming stars. Certainly, galaxies do run out of gas over time, or they go through the gas supply, and the gas densities go down with time, but it's not enough to explain the population of red and dead ellipticals. As for the spiral arms, surprisingly, that is still not entirely known. So the gravity wave theory that you referenced is still the dominant way of interpreting spiral structure, but there's debate. And in fact, it's interesting to try to simulate disk galaxies and try to get their spiral structure right. I think it's amazing that that's still a hard thing to do. But there's uncertainty, I guess, is what I'm trying to say. And for the really well-defined spiral arms, the two spirals and the m=2 mode spirals, those are understood, and we know that that's usually an excitation caused by a companion galaxy. But the more flocculent spirals, still not completely understood. But we know that spirals that spiral structure needs to have a disk. And so the appearance of spiral structure is telling you that there's a disk involved. And star formation happens typically in a disk component as well. So something in that transformation, and I think your question is what's getting rid of the spirals in the red and dead ellipticals? It's something to do with getting rid of the disk. And the ellipticals don't have that disk shape. It's still there though, but not as dominant as it is in the spirals. And that may also be related to something about the gas. If you could puff up, heat up, blow out the gas, get rid of the gaseous disk component, you wouldn't see the spiral structure as well. So that may be part of the story.
May I ask a question? Can you hear me?
Yes, go ahead.
Oh, very good. Years ago, I thought I understood that the ellipticals became larger and larger by looking at the Virgo cluster, which has lots of them in it, big, huge, enormous ones. And they merely ran into each other and got bigger, and they get run into by another and got bigger yet. And I hadn't figured out some of the things that you had discussed tonight. So first, a spiral has to be at the point of not making stars and run into another elliptical or other galaxies. In other words, if Andromeda hits Milky Way, would we then be on the way to massive new starbirth, or would we be on the way to being an elliptical? I don't understand the two theories, which is sort of basic to what you're looking into, and you're looking into beyond all that too, of course. But
right. So, I mean, that's another great question. The answer is both. Mm-hmm. So when Andromeda hits the Milky Way, we think there will be both a burst of star formation because all of that gas gets sort of jiggled up and disturbed, and that leads to collapse, which can form knots of increased star formation. But then the theory is that the merger itself will eventually lead to a red and dead elliptical. So for a long time, to go back to Mrs. Self's questions, the hope was that mergers between spirals was the way that you formed ellipticals. Right. And I didn't tell that story because we're not sure that it's true anymore. It was a really nice story, and the idea was that you have two disks, two spirals, they come together, and they don't have the same orientation in their orbits, of course, just random, they're coming in at random angles. And so the gravitational interaction disturbs the disks, and you end up with a stellar configuration that's more round. We see that in simulations. So that's how you could get the morphology of an elliptical. And then maybe you trigger some catastrophic event like a quasar or something happens at the same time that blows out the gas, heats up the gas. You've got to get rid of it, because if you don't, the gas will come back and form a new disk and make new stars. And so that's still the part that is uncertain. When people like me went out and tried to observe and confirm that theory, we couldn't find enough mergers. We found ellipticals that still had disk structure, even though they weren't forming stars. We couldn't find the quasars in the right place. They weren't always in galaxies that were in the middle of transition. And so the story just hasn't really hung together. It's a good story, but it seems more complicated than that, which is part of why we have to back up as astronomers and admit that it's more complicated than we might have thought, say, 10 years ago.
Mm-hmm. Thank you.
Well, thank you for an excellent talk.
Thank you very much.
Well, I guess I do have one question. That has to do with the huge amount of data. How is that going to get processed?
Silicon Valley to the rescue once again. You know, Google is actually a partner in LSST, as is Microsoft. And so there's a lot of interest in trying to use large data processing expertise from internet companies to handle the flux of data. But it's a big problem, and it's one that has been on people's minds for many years. And so there are actually simulations of the data flow, and people have been preparing the pipelines and the data reduction routines for years, even though the Rubin Observatory is not coming online until I think it's 2023 now. So there's been a lot of legwork to try to get ready. And I think we will be ready from the data perspective, I think. I'm not sure that the community is ready from kind of the mental, emotional perspective of what all that data is going to mean for us. And we're certainly not ready on the spectroscopy follow-up, which was my soapbox tonight.
Okay, thank you.
Thanks for the comments in the chat window too. I appreciate that.
Do you want to give us the reference to some of your articles?
You know, these days it might just be easiest to search for my name. I think Google will land you there as fast as I can. I would use Google to get the links for you. But I would, I'm very proud of a paper 2016 in Nature that's on the discovery of red geysers. And so that's a good place to start if you're interested in a little bit more background on this talk. And the first author was my postdoc, Edmund Chung, here, I'll put it in the chat, C-H-E-U-N-G, Chung et al. I'm the second author, that's 2016. And so that's a paper in Nature, which is written at a level that I think everybody can understand on this call. It's not supposed to be a very technical description for other astronomers. So that might be.
Could you repeat the spelling of the first author?
C-H-E-U-N-G.
C-H-E-U-N-G, okay.
And if you would like to be inundated with the astronomical literature on this topic, you can search for galaxy quenching. That's the jargon that we use to describe the shutoff of star formation. We call it quenching. So
quenching, you mean like quenching something with water?
Right.
I've forgotten how that's spelled. You know, the older I get, the less I know how to spell anything. I seem to forget how to spell things.
I think spell check is doing that to me. Quenching is Q-U-E-N-C-H-I-N-G.
Yeah, that's what I saw. It just doesn't look right. Okay.
You'll be happy to know that you can see this also. It's archived, so you can go to SFAA and just ask to hear this talk again, which is really very useful to be able to go over it again and have it sort of sink in a little better, a little more. But almost every speaker we've had in quite a few years has been archived. And so when you go to our website and look at archive, you should be able to find tonight's talk. And I'm so very grateful we can do that because there's lots of information we heard tonight.
That does sound like a good idea.
Yeah.
What is your website again?
SFAA-astronomy.org. And it'll take you to the website, and there'll be a little sidebar that'll say archive.
Yeah, I think it's on the lectures.
The lectures page.
Yeah. So.
Yeah.
And then you can then see. That will take you to YouTube and where they're actually saved at.
So that's very good.
Yeah, we have from 2016 till
that sounds good.
this year on there.
Oh, yeah. Yeah.
It might be better than just reading Nature to go over this again.
Yeah, and we have also recorded on the camcorder 2015 and maybe 2014. We just don't have the time to encode it all and upload it to YouTube. It's quite a challenge to upload the older videos, but we do have them.
Okay.
Kevin, I appreciate so much your extremely interesting talk.
Thank
And
you
your
very
slides. Your slides help to really organize it, and it just really looked terrific to help understand the scope of the size of those fibers. Oh my goodness, what a challenge that was. But yeah, Silicon Valley to the rescue.
Let's hope so.
Yeah.
Well, thanks for the opportunity. I'm sorry that we don't get to interact in person, but maybe another time.
I know. Well, definitely there has to be another time because you're going to have more to tell us in the future.
That's for sure.
I
That's
know.
for sure.
We'll hope to take you to dinner and, have a lovely auditorium full of people that you can speak directly to.
I look forward to it. But it was lovely to be able to talk with all of you and hear what you're all interested in.
Mhm.
So enjoy the fireworks display with Saturn and Jupiter.
Ah, yes. Yeah. Thank you very, very much.
Thank you
Yeah,
so
so we-
much.
So we have quite a number of people saying thank you for the talk. Very interesting. A lot of food for thought. Super interesting. Yeah, definitely. A lot of people want to thank you.
I appreciate it. Thanks, everybody.
All right.
Thank you.
Thank you.
Bye-bye.
Bye-bye.
Happy
Bye.
holidays. Bye.
Good night.
Happy